Welcome back to this series where I teach you how compilers work. In the last video, I showed you how to make variables. If you didn't see that, then I think there's something actually wrong with you. It's a series. How are you going to follow along in this video without seeing that one first? Never mind that, however. I hope you actually didn't follow the last episode, because that code would actually never work. The reason being that every time pretty much anything happens, the first variable you wrote will be overridden. You don't want that, probably. So, to start things out, I will show you how to make an instruction optimizer. I have shown you previously that you are able to do movq to move a quad word from one place into another. This operation is very useful and very important and shows up pretty much everywhere. A push and pop instruction in our compiler will also be everywhere, just not in a good way. If you really think about it, a push and pop operation next to each other is functionally equivalent to simply moving something, and you'd be exactly right. That's why instead of what I led you to believe last episode, we will be implementing an optimizer first. First step of making this is to replace each instruction from a string form into a form that can be manipulated directly. If you use TypeScript, you might want to use an interface. Considering how everything is an object, it just makes sense. In C++, memory is very literal, so we could just use a variant. A variant takes in a bunch of types, and is basically the same thing as a union, just slightly better or something. I don't really know what I'm doing in C++ most times. In our implementation, an instruction will hold a variant over all the different types of instructions that we'll have. Next, we can create the actual instructions, those obviously being a push, a pop, and a move. This is what we will start out with. We can populate each of these with simple string members. For pop, you can make a where to pop or destination field. For a push instruction, you can make a what to push or source field. For a move, you can include both a source and a destination. Additionally, you might remember how I explained what the different sizes of integers are, like the 1 byte, 2 byte, 4 byte, etc. We will be implementing these later, so let's create an enum class called a data size, or something similar. Populate this enum with fields like byte or char, short or word, int or double word, long or quad word, and in the future, when we implement floats, we can put float or SS and double or SD. Don't worry about those abbreviations, I'll explain it when we get around to that. Need that enum data size to be a field in the push, pop, and move instructions. The very last instruction we will add is a literal instruction. This doesn't correlate to any one instruction that x64 actually has, but rather is a simple string that can be placed literally into the output assembly file without being manipulated by an optimizer. We will put things like labels, linker directives, and syscalls here, because they are so few and far between that they do not warrant an entire struct just for them. Every time you have an add to file function or something like that, instead you should be pushing an instruction. We could put these instructions anywhere, but a C++ vector makes the most sense, as it is ordered and can contain many different kinds of instructions. Each push q plus and then whatever could be replaced with a push instruction. Same thing for pop instruction, move, or all those other ones. If you have all of this handled, then you're ready for the next step. The next step is to convert our instructions back into strings. This step is very simple. Make a string variable that every stringified instruction will be placed onto. Then, use an stdvisit to check what type of variant has been used, and depending on that, we will push it again. For example, in the push visitor, we will simply add a push q, a space, and then whatever is in the field. That's it. Now, you should be able to move that stringified output into whatever file you need. Hopefully, if you run your program again, your code should look exactly the same. If that somehow worked, then good job. You did everything correctly. If you didn't, then it's your code, not mine. Just go back 2 minutes and listen to me talk again. After all that work, what's even the point? The code still doesn't work. We haven't even implemented the optimizer yet. Well, luckily for you, that's exactly what we're doing next. The optimizer will take in our vector of instructions and return a new vector of instructions. This new one is our optimized one. In our optimizer, we will loop through each pair of adjacent instructions, and if they are a push immediately followed by a pop, we will remove both instructions and replace it with a move, where the move's source is the push instruction and the destination is the pop instruction. Before we push the optimized move instruction, we have to check if the push instruction and the pop instruction don't both have offsets. A move instruction with an offset for both its source and destination is not valid in x86, so we will move it to a temporary register first. We will simply put the push instruction in a temporary register like R13, and then move that value of R13 into the pop instruction. And thus the code in the optimizer to do this should look like this. Assuming you didn't just break literally everything, your program should still be able to compile, and now, instead of looking at gross push-pop pairs that are barely readable, you can now see very clean moves. Hopefully, now that nothing is being dealt with directly on the stack, this means that your variables should finally work and not be annoying. All that work just to make it start working again. But now we can get to the fun part. We can now implement all those different adds, multiplications, and divisions that you so very much desire. An add instruction in x64 looks something like this. Add Q, RBX, RAX. If you remember how the left side modifies the right side in AT&T syntax, this will be adding whatever is stored in RBX onto RAX. So you could imagine it as RAX plus equals RBX. This just means that whenever you get to your expression that handles adding, in your language you may have done a binary expression or an add expression, I don't mind. It will evaluate the left-hand side, pop it, then the right-hand side, then pop it, then do the add, and then push the result. That should really just be it for adding. Subtracting works very similarly. The subtrahend, the amount that you subtract, is in the left side of the instruction, and the minuend, the amount you subtract from, is on the right. Multiplication and division are very difficult though. Instead of having two different sides that you can see and edit, the number you do the operation on and to is hidden, and is always rax. Please note that this is only for unsigned divides. We have not covered signed integers yet, so be patient, we will get there. Multiplying RAX by 5 would look something like this. Mul Q 5, which you can assume is the same thing as RAX times equals 5. So this means that you will always pop the left-hand side into RAX, the right-hand side into whatever register you'd like, and then you would just push rax as the result. Division works in pretty much the exact same way. Please note though, because we do not have floats, a division instruction will be like how you divided in 2nd grade. Decimals don't exist. The quotient will be in RAX, but the remainder, if there is one, is in RDX. Also, please note, the division instruction was designed to work on really big integers that span 2 registers instead of just one. This means that the number that you will be dividing is actually stored in 2 separate registers in case you have a really big number you need to divide. However, since all of our numbers are the same size, 8 bytes, this means that the register that stores the bigger half should always be 0, so that way our output doesn't get insanely messed up. So, you could do this simply by moving 0 into RDX. RDX is the register that stores the larger half of the 2 registers. RAX is what actually stores the number you divide. So your implementation for division should actually look exactly the same as the implementation for multiplication, except you will actually add a move Q0 RDX before you run the division. Then you can just simply push REX, and that's division. I really hope all of that made sense to you. If you're ever lost, you can just use any compiler or disassembler and make a very simple C program for dividing or adding or multiplying by another number. Just a side note, in case you ever want to actually do this, C, as the very old and very optimized language that it is, knows of faster algorithms to compute simple divisions by 2, 3, 4, 5, etc. These examples usually do not include a single divide. Please be aware of that. You do not need to implement these fancy optimizations in order to have an awesome language. Arithmetic is quite the challenge to implement in this simple little language, isn't it? What do you do if your program has mysteriously broken? You would need to debug it in a tool like GDB, LLDB, etc. However, it's actually really complicated to implement. So how might you go along with adding debug symbols to your language? Well, you're gonna have to wait for that, because now it is time to end the video. I hope you still learned something new today. Come back soon for the next installment of Writing Our Compiler, and please subscribe so more curious people like you can see this video and learn something new themselves.